In mathematical physics, the de Donder-Weyl theory is a generalization of the Hamiltonian formalism in the calculus of variations and classical field theory over spacetime, which treats the space and time coordinates on equal footing. In this framework, the Hamiltonian formalism in mechanics is generalized to field theory in the way that a field is represented as a system that varies both in space and in time. This generalization is different from the canonical Hamiltonian formalism in field theory, which treats space and time variables differently and describes classical fields as infinite-dimensional systems evolving in time. De Donder-Weyl formulation of field theory. The de Donder-Weyl theory is based on a change of variables known as Legendre transformation. Let xi be spacetime coordinates, for I 1 to n with n. For representing 3 plus 1 dimensions of space and time, and Ya field variables, for A equals 1 to m, and L the Lagrangian density L equals L y A I y A x I. Display style L equals L y caret a partial underscore I y caret a x caret I, with the polymomenta p are defined as p a I equals L I y a. Display style p underscore a caret I equals partial L partial underscore I y caret a, and the de Donder-Weyl Hamiltonian function h defined as h equals p a I y a minus L. Display style h equals p underscore a caret I partial underscore I y caret a L. The de Donder-Weyl equations are p a I x I equals minus h y a y a x I equals h p a I. Display style partial p underscore a caret I partial x caret I equals partial h partial y caret a partial y caret a partial x caret I equals partial h partial p underscore a caret I. This de Donder-Weyl Hamiltonian form of field equations is covariant, and it is equivalent to the Euler-Lagrange equations when the Legendre transformation to the variables p and h is not singular. The theory is a formulation of a covariant Hamiltonian field theory which is different from the canonical Hamiltonian formalism, and for n equals 1 it reduces to Hamiltonian mechanics. See also action principle in the calculus of variations. Hermann Weyl in 1935 has developed the Hamilton-Jacobi theory for the de Donder-Weyl theory, similarly to the Hamiltonian formalism in mechanics formulated using the symplectic geometry of phase space. The de Donder-Weyl theory can be formulated using the multi-symplectic geometry or polysymplectic geometry and the geometry of jet bundles. A generalization of the Poisson brackets to the de Donder-Weyl theory, and the representation of de Donder-Weyl equations in terms of generalized Poisson brackets satisfying the Gersten-Haber algebra, was found by Konachikov in 1993. History. The formalism, now known as de Donder Weyl (DW) theory, was developed by Théophile de Donder and Hermann Weyl. Hermann Weyl made his proposal in 1934, being inspired by the work of Constantin Carathéodory, which in turn was founded on the work of Vito Volterra. The work of de Donder, on the other hand, started from the theory of integral invariance of Élie-Cartan. The de Donder Weyl theory has been a part of the calculus of variations since the 1930s, and initially it found very few applications in physics. Recently it was applied in theoretical physics in the context of quantum field theory and quantum gravity. In 1970, Jedrzej Sniatycki, the author of Geometric Quantization and Quantum Mechanics, developed an invariant geometrical formulation of jet bundles, building on the work of de Donder and Weyl. In 1999, Igor Konachikov has shown that the de Donder Weyl covariant Hamiltonian field equations can be formulated in terms of Duff and Kemmer-Petty matrices. See also: Hamiltonian field theory, covariant Hamiltonian field theory. Further reading: Selected papers on geodesic fields, translated and edited by D. H. Delphinek. Part 1, 2, Part 2, 3. H. A. Kastrup, Canonical Theories of Lagrangian Dynamical Systems in Physics, Physics Reports, Volume 101, Issues 1–2, pages 1–167 1983. Mark J. Gautier, James Eisenberg, Gerald E. Marsden, Richard Montgomery. Momentum Maps and Classical Relativistic Fields. Part 1, Covariant Field Theory. 4. Cornelius Paufler, Hartmann Romer, de Donder Weyl Equations and Multisymplectic Geometry, Reports on Mathematical Physics, Volume 49 2002, No. 2–3, pp. 325–334. Christoph Morin, The Riemann Legacy, Riemannian Ideas in Mathematics and Physics, Part 2, Chapter 7.16 Field Theories for Calculus of Variation for Multiple Integrals, Kluwer Academic Publishers, ISBN 0-7923-4636-X, 1997, p. 482 ff.